Alright, okay, you're welcome back once again to today's class. In the last class, we tried to look at topological space, subspace of topological space, open set, closed set, and the like that. Now, today we want to actually go into set operations in topological space. Set operations. What are those things you have to consider? We want to considering what we call accumulation points. Accumulation points. Consider accumulation points. Or we call it cluster points, because some call it cluster points, or some call it what? Limit points. Limit what? You have accumulation point, cluster point, and some of them call it limit cluster point or limit points also. Even some call it derived, also derived points. Also derived as well, derived points. So derived points. So those are the ones we consider today, and then we look at some closure of the sets. Then we look at interior point, exterior point, and boundary of a set. Now, before we start today, let's look into accumulation point. Now, what's our accumulation point? Now, we have what? Accumulation point. Accumulation what? Point. What does it mean? Number one is that let X be what? A topological space. Consider let X be a topological space. Then a point P in X is an accumulation point. An accumulation point. Of a subset A of X. How's that? If every open set, look at it, if every open set G, I got that, containing P, I got that, contains a point of A different from P. Consider that. Now look at it. What does it mean? It's like if you have a topological space, a point P in X is an accumulation point of a set A of X. If every open set G, that is for every open set, that is for every open set G you have in that topology now, there exists another point containing P, that open set contain P of a point P, and also of A different from what? From P. What do we mean? That if G is open, I think you pick G is open set, P is P from the ground, and then that point is in what? Is in that G. I know that. So it now implies that you now have G, you are removing P, that it does not contain P now. Those open sets do not contain P. Intersection that A must give us what? Is not empty. So when it's not empty, then we can say that what is called an accumulation point. That is, this P now is an accumulation point. So the set of accumulation points of A denoted by A prime is called the what? The derived set. So that you can say that derived set. You can say A prime, or sometimes we derive A raised to power D. Also, people will pick it as what? Or AD. It depends on the notation of each of the textbooks that we can. Whatever we are using now is taking what? A prime or A raised to power of D. So these are called a derived set. Now, how do we determine that? Based on this definition now, it's like if you have, let's look at this assignment. Look at this example on this. Let's look at an example on this now. Let's look at an example on this. On the accumulation points on the set. Now, what does it mean? Look at it. The class. Let's are doing the class. Let's say you have tau. That is, tau is given as what? x, comma, empty set, set A, comma, set C, comma, D, comma, then A, C, D, comma, then you have what? B, C, D, E. So this is the topology that we have now. Defines a topology on X, and X is what? A, B, C, D, E. Try to go with F next now. Now consider the subset. The subset A, which gives us what? To be A, B, C of X now. Now, let's check which one. Let's go back to the definition of. I want to use that definition to understand what we're touching. You know, we said that for accumulation points now, P being an accumulation point. I think we are not saying that accumulation points. We are saying that if you pick G, is a member of that tau. I got to use an open set now. Then and your P is in what? Is in G. Then it implies that G, if you remove that P out from it, intersection A is not an empty set. So this is one to use that. Which of the points here will give us an accumulation point? Now, we know that this guy is subset of X, ABC. That's true. Now, what to do just that? That was just something. You know, let's start with P. Let's look at those who are having B. No, A is here already. I mean, good. Now look at this place. What are the one elements that give us the accumulation point now? Now observe that no, B is an element in X. Let's speak from B. B is an element in X. So is a what? B is an element that is a limit point or accumulation point. It's a limit point or accumulation point of A. Why? Since you can see that B is here. Now, since look at it, since the open set containing A, containing B are what? Containing B are what are those that are containing B? They are just this one, and X are what? B, C, D, E, and what are those sets? X. That's why they continue what a limit. Give you a limit point because those are the ones that are containing B and X. They are one containing B and X now, and each contain a point, and each containing a point different from what? Different from what? Different from B. How? Look at it. If you remove B from here, we have CDE. CDE intersection A. Look at this. CDE intersection A now. What do you have? That is, if we are trying to say that, you know, this, let's start from B. B is the main point of it. That is all the elements from here. Whether they are main point or not. Now, if we now pick, look at it now. If I have, you know, based on this definition, I know my G. My G is now A. My G is B, C, D, E. I mean, that's my G. Now, if you're now removing this G slash B from it now I'm going to have something like C, D, E. I got that. So C, D, E now intersection A. Which your set A is what? A, B, C. What do you have? I have C. T is common out. So which is not an empty set. That is why you can see that B is a what? Is a limit point of that set. So if this one gives us an empty set here, we cannot talk about B is not an accumulation. It's not an accumulation point. I got that. So we have C there. So that means is what? Is an accumulation point. Now the second one is this. Now the same thing for X. Now if you pick your G to be A, B, C, D, E. That's your X, Abi. Then you know that if you remove B from it, X plus B. What do you have again? I have B, C, D, E. Excuse me. Intersection with what? With A. And A is what? A, B, C. What do you have again? I have B, C, which is what? Not an empty set. So definitely now B is what? Then B is an accumulation what? Accumulation point. So that means B is an accumulation point in that line. Now, but check something else here. Let's check other point A. Let's pick point A now. Is A an accumulation point? If you are picking, what are those open sets? What are the G's? What are those G's in this table that contains A? Which are what? We have X and we have set A. Can you see that now? I think we have X and we have what? A, C, D. Can you see that? So by the time you are moving A from here, what do you have? Empty set, and then it's an empty. So that will give us, it's not A is not a what? It's not an accumulation point. And on the other hand, the point A here is not a limit point of A, since the open set A, which contain A, does not contain a point of A different from what? Different from A. So similarly, D and E are limit point of A. Consider that. Now let's go to C and D also. If you consider C and D also, let's check it out again. Is D a limit point and D a limit point also? Let's check D. Is D a limit point? D now. Is D a limit point? Let's check. Those open sets that contain D are what? We have C, D. Then we have A, C, D. And then we have what? B, C, D, E. Now, these are the open sets that contains what? That contain D. Which are the open sets? I want to check whether D is an accumulation point or limit point or derived point now. So when you look at it now, from here, if I have G slash D, I remove D from here. I'm going to have C, Abi, and the C intersection A. What is C intersection A now? That is our A is what? So I wrote it out. A is our A is ABC. A is what? ABC. I got it now. So let it intersect C intersection ABC or ABC. What do you have again? I have C, which is what? It is not an empty. I got that. So the second one, that's for D now. Let's pick this one again. G slash D. Remove D from here. Now what do you have? I have AC. How's that? So at AC intersection A will give us what? A, C, which is not an empty. Then lastly, G slash D. Then remove that one also. I have B, C, E. Intersection with A. What do I have? I have C. I have BC, sorry, which is not an empty. So also therefore D is what? Is a limit point or accumulation point or derived point. So those are means that this also using the same procedure also. So therefore the limit points are what? They are B, D, and E. So your derived point now, your derived set, that's AD now, will now give you what? B, D, E. So it goes the set of all the accumulation point or limit. So that's how you can actually find an accumulation point and the derived point of a set. Now, let's move on to closure of a set now. Closure of a set. How do you determine that? Closure of a set. Let's talk about closure. So let's look at the closure of a set now. It's a closure. Closure of a set. Now, whatever is closure of a set. Now, let's say that let A be a subset of X. I got that of a topological space X of a topological space. Can you see that? Let's be a topological space X now. The closure of A denoted by what? A bar, or you can call it, let's say the bar A bar, let's use A bar now, is the intersection, look at that, is the intersection of all closed supersets of A, is that of all closed superset of A. That's meant by what? A closure of a set. What does it mean? If you have Fi and your I, so that I is what? In this place, in this interval, that you have this set now, is the class of all closed subsets of X containing what? Containing A. Then I can now have the closure of A is what? Subset of what? All the Fi. Closure of that, all the Fi. So that reverse as what? The closure of a set. That's what as the closure of a set. That is the intersection of all closed supersets. Closed supersets of A. Closed superset of A. So if you have this, I said, then intersection of all these Fi that will give us the closure of that set. And let me give you one example on that. Now, what can we see? Look at this example now. For example, let's note that one. Look at the example. Note something that Fi. Let's check this one out. Fi, so that I what is the class of all closed subsets of X containing what? Containing A. That is your closure of a set X equal to I equal to 1 in I of Fi. So that is what we have. Now let's look at this example. Look at this example for the closure of a set. How do we determine the closure of a set now? How can we determine closure of the set? So, and it's very simple to determine that. What to do is just this. And let's check it out. Note something that your closure of a set is a closed set. Since it is the intersection of all the closed sets. No, we have explained closed set in the previous lesson that they are when their complement of that set are open. So we have what? A closed set. Now, today we don't look at closure because it's a closed set now. Definitely now we cannot have something like your closed set A is a subset of what? Closure, sort of what? F. Note this one also. So those are the principles that we have here. The that I can have a proposition here that a set, look at it, a set A is closed if and only if and what? Only if your A is equal to the closure of that set. That is, you can have a proposition that says that a set A is closed if and only if A is what? Is equal to the closure of that set. And you can now make it a position now, or a lemma. You can make a position now by saying that let A bar be the closure of a set A. I go to that now. Then, one, you can say that A bar is closed. You can say that two. You can say that if F is closed, superset of A, then I cannot have A is the sum of what? A bar sum of F. Can you see that now? Now, thirdly, and if A is closed, if and only if and only if A is equal to what? A bar. So that is what we have here. So A is closed if and only if it's what? A is not given. So these are the results that can actually used in solving or closure of a set now. Now let's look at this simple example to illustrate this theorem that we just written out. To illustrate this one out. Let me look at the example like that. And what the example says that said consider the topology. Consider the topological on X. So on X, which is same as on X, and your heading as what? A, B, C, D, E. How see that? I got that. So we are the closed, look at that, the closed subset of X are what? What are the closed subset of X now? You know, I told you that we are given a topology now. You know, topology that we have been using earlier. Now, the topology of this. The topology I want. You know, the topology we have already is this. Empty set, this, A, C, D, A, C, D. We have what? B, C, D, E. So you have this topology now. So we have this topology. Now I have this topology on ground now. So what will be the closed set of this topology now? Of each member of this one will give us a closed set. And find the complement of this one. So the closed set are what? They are now what? This. Look at the closed set. Empty set X. We have B, C, D, E. Then we have what again? A, B, E. Then we have this one. What do we have now? We have B, E. And lastly, we have A. So these are the closed set. Now, what will be the closure of your set B? Let's start. The closure of B is what? Based on the definition I have, that we are saying that the class of closed set subset of X containing A. What is contain what? Contain A. So what we need to do is just this. So now the closure of B, what is the closure of B here now? That contain the highest one is a subset of that, so it's a subset of it, and it contains A. It contains A. So that it contains A. So what are the closure? So what are the closure of A now? A is a subset of this, a closed set of this one. That's all. Now what are they? Let's start with B. The closure of B will give us what? It contains B also. What are they? We have BE. We have B, comma E. I got that. For a closure of AC, A, comma C, we have what? We have to do what? To set X. The whole set will contain that one now. For the closure of BD, B, comma D, we give us what? B, C, D, E. Can you see that? So because here it contains B, the superset, look at that, it said the intersection of the superset of F. What are the Fi that contain that B? Fi that contain B. You know, here I have this one is a closed set, I mean, intersection with X, we have this. Intersection with this, well, intersection with this. I think what I'm trying to say is this. For your B, for this closure of a B now, is something like what are the superset? Intersection of all the superset that contains B. What are they? We have X intersection what? B, C, D, E intersection A, B, E. I know that. Then intersection what? Intersection B, E. Can you see that? When you close this, what are they? What's intersection with all this? What do you have? You close that B. will now give us BE is what that is close to both of them. So we have a BE there. Can you see that? So the next one, if it is BD, what are those that contain BD? BD, for total of BD now, those that contain BD, this one contain BD, we have X intersection B, C, D, E. What other one that contain BD? No, not one again. So that means we are now having those supersets. This give us what? This now give us BC DE. Can you see that now? So that means the closure of that one is this. So if it is for AC now, for AC, what are the one that contain AC? S intersection. What other one that contain AC? We have single A, we have this. We have ACD, but it doesn't contain AC here. Only it does not contain, so we cannot pick that one. So the answer will give us only the X that we have there. So that's about the closure of the set and the accumulation point of the set. So thank you very much. Have a wonderful time. Bye bye.